All right, let's get rid of this so we don't have the seizure mode. All right, so 10.7 is kinetic molecular theory. Anybody remember what kinetic means, refers to? What type of energy? What's that? Yeah. Movement. Good. So kinetic is referring to basically anything that's moving, any kind of moving energy or movement energy. Okay. Um, so kinetic molecular so it's basically referring to the movement of molecules, was developed to explain gas behavior. Now, we use kinetic molecular theory in Chem 1 as well. I don't know if you guys remember when we talked about like solids, liquids, and gases, and we talked about like how close together or far apart the molecules are. Yes? No? Some of that? Okay. So like the more energy they gain, the more the molecules move, the more they spread apart, and the faster they move, right? Like that kind of stuff. That's kinetic molecular theory. So um, you've already sort of been introduced to it, and you kind of know some stuff about it. Now, in terms of gas behavior, uh, so like again, we've had some of these, so just kind of reminders. Gases consist of a large number of molecules in constant, random, rapid motion. So gas molecules are always moving, they're moving quickly, and there's no real pattern to their movement. They just sort of travel out. Generically, they'll travel in a straight line until they hit something, and then they'll bounce off and head somewhere else until they hit something, and just like ping pong all over the place. Okay. Um, the combined volume of all the molecules is negligible. That means like basically it's so small it doesn't really matter or doesn't really affect anything compared with the volume of the container. So that's talking about the actual volume of the actual molecules versus the whole volume of the container, because there's so much air and space in between them, right? Intermolecular forces. Now, we talked, okay, if you had Chem 1 with me 2 years ago, we talked about this. If you had it with me last year, we didn't really talk about it much because this was during COVID. But intermolecular forces are the forces between the molecules themselves. All right. And so what happens is as molecules slow down, their energy slows down, they get closer together, the intermolecular forces or forces between the molecules grow. The thing's sort of like causing them to sort of stick together or hold together. You can kind of mentally think about it if you're trying to get an idea. Have you ever seen like water drops on a windshield, and like if it's raining or something and water drops on a windshield, and as they like trickle down, they'll sort of be attracted to each other, and they'll kind of like almost like what's like Terminator, like bleb together, like, and they'll like form a bigger drop, and then more of them will join it, right? Like, and it's because there is some level of attraction between the molecules. So like you can sort of think about molecules when they're going slower and getting closer together, they do have forces, intermolecular forces that kind of help hold them together. Okay. But in gases, because gases are moving so fast and they're spread so far apart, those intermolecular forces they don't really count. They're not really counted. They don't really affect them. Okay. All right. So we've talked about some of that. Energy can be transferred between molecules during collisions, but the average kinetic energy is constant at constant temperature. So what this means, average kinetic energy is the average moving energy. So if two atoms collide, whatever one loses, the other one will gain in terms of the energy. So overall, there's no energy loss. It can transfer from one to the other, but there's no overall energy loss in it. Okay. Collisions are perfectly elastic. So we talked about the Newton's cradle thing earlier, right? Yeah. I know some people. Okay, so just as a refresher, the the Newton's cradle, when you pull one of the balls back and you let it go and it hits the others and then it kind of travels through and they bounce back and forth, right? In real life, the Newton's cradle will slow down. We said because of what? Friction. Yeah, good friction, right? Air friction, transfer, like incomplete transfer, like when friction between the balls as they strike, air friction, all that stuff. But with molecules of gas, remember, the collisions are perfectly elastic. You don't lose any energy. Okay. So the average movement energy, kinetic energy of gas molecules is proportional to the absolute temperature. When you take the temperature of something, really what you're getting is an average measurement of the movement energy of the molecules. Because you're measuring heat, which comes from the friction and movement of the molecules. So when you measure temp, you're actually measuring sort of an average of the kinetic energy. Okay. All right. So now here's some stuff that might be new to you. Pressure. Where does gas pressure come from? It results from the collisions of the gas molecules with the walls of the container. The magnitude or amount of the pressure is determined by two things: how often and how hard the molecules strike the walls. So what this means is there's two ways that you can affect the pressure of an enclosed gas or a gas in a certain area. One, you can make the molecules strike the wall more often or less often. That'll change the pressure. Or two, you can make the molecules strike the walls harder or softer, and that'll change the pressure. Make sense? So two different things. Okay, so let me ask you guys this. So think about gas in like a closed container. Okay. What would make the molecules strike the walls more often? Like what could you do to the molecules? Like heat it up somehow. Because what's heating it up going to do to the molecules? Make them do what? Increase movement. Make them go faster. Yeah, good. So if you heat it up, you're adding kinetic energy, you're going to make the molecules go faster. So if you change the speed of the molecules, they will collide more often. Or if you slow them down, they'll collide less often, right? Okay, so temperature is going to be related to the speed of the molecules. That will make them strike more often. Okay, now how hard the molecules strike is going to be based on some other stuff. So the pressure will change with the strike. But how would you actually make them strike harder? Okay, good. So if somehow like the differences in mass could cause it to strike, like basically if you think about momentum, right? Like if you've got two molecules traveling at the same speed, but one is bigger, think about two cars traveling at the same speed, but one's bigger, it has more momentum, it's going to strike with more force, right? So effect like having the differences in mass could cause it to strike with more force. Okay, that would be one example. So the one thing is a lot of times we think if we heat it up, like if they're going faster, they're going to strike the walls harder. But in the case of gases, that's not necessarily true. Like speeding up typically affects how often they strike. So it's like striking more often, which means that's going to increase the pressure that way. Okay. All right. So, blah, 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 blah. This is basically just saying that within any given sample of gas molecules, there's some that are going to be traveling faster, some that are traveling slower. The temperature, the average, like the temperature of something is an average of all the different ones, kind of. That's all it's saying. Um, okay, as kinetic energy increases, the velocity of the gas molecules increase. So there's something called root mean square, or RMS speed, which is designated by variable u. Okay. It so the reason I have page so oh sorry, hold on. The reason I have page 415 at the bottom is that's just you don't really need to know this. This is just the if you were interested at all, some people who are interested in kind of the derivation of the math of it. Um, hold on, let me get there. Okay, so like so this shows the derivation of the difference between RMS speed and average speed, like how the difference in how they're calculated. So if you're really interested in the math of it, like this breaks down the difference between average and the RMS. I don't care that you know that in terms of what I want you to know. So that's just more of like FYI type stuff. Okay, so the RMS speed equation, average kinetic energy, is related to RMS speed, is this equation here. The cursive E, I forget what, I think that's actually a Greek symbol, I can't remember, but so like the cursive looking E thingy equals 1/2 mass times RMS speed squared. U is the RMS speed. Right? So really, I'm not going to ask you to do much more than be able to like plug in two of these three things and figure out the other one, which is just basic algebra. So, all right, the application to gas laws. So this is where this stuff really actually comes into play in terms of the actual like conceptual understanding of this. So I highlighted the two things: effect of an increase in volume at a constant temp, and effect of an increase in temp at a constant volume. All right. So as volume increases at a constant temp, the average kinetic energy, there was a misprint in there. So yours, I think I gave you guys copies of what the energy I already put in, right? Okay. The average kinetic energy of the gas remains constant. Therefore, U is constant. However, volume increases, so the gas molecules have to travel further to hit the walls of the container. Therefore, pressure decreases. So if the molecules are going the same speed, but you have more room for them to travel in, they're going to hit the walls less often, right? Not as often. That's going to lower your pressure. Okay, so here's where the weird thing, this is what's going to sometimes throws people off though. Your temperature doesn't change because the average kinetic energy stays the same, but the pressure drops. Okay, that weirds people out sometimes because a lot of times people always think about temp and pressure as like, I mean, and they are related, but you can actually, here you're manipulating the pressure by changing the volume, and you're actually keeping the temp, because it's the average kinetic energy, the same. Okay. All right. Second one, effect of an increase in temperature at a constant volume. If the temperature increases at a constant volume, this is the one we were kind of talking about already, the average kinetic energy of the gas molecules increases. So you're literally making them move faster. There are more collisions with the container walls. Therefore, U, RMS speed, increases. There's a change in momentum in each collision increases, the molecules strike harder, therefore pressure increases. So Let me summarize what this is telling us. If your volume changes and your temp stays constant, your average kinetic energy doesn't change. Everybody get that? If you have a volume change and a pressure change because of the volume change, but if your temp stays the same, that means your average kinetic energy stays the same. So your RMS speed does not change. Okay. So the molecules are hitting the walls more often or less often because what? Because you're changing, what's that? You're changing the amount of space they have to move in, right? So if you think about like if you threw a bunch of bouncy balls into a bucket and they were all moving the same, they were moving the same speed. If you took like a 5 gallon bucket, right, threw them in there and they were hit like however many times they'd hit the walls of the bucket, then you took those and you put them into like one of those small little like the little handheld like half a gallon buckets or whatever and put them in there. If they were still going the same speed, they'd be hitting the walls more often, right? But not because they're going faster, because the walls are closer. There's less room to move it. Does that make sense? So the pressure here is the energy does not change in this example, but the pressure will change. Okay, because you're manipulating the amount of space they have to move in. The second one, the pressure changes as well in the second one. Pressure changes in both, but for different reasons. In the second one, the pressure changes because you're changing the speed of the molecules, changing the temp, which is then going to change the pressure because the molecules are hitting the walls more often and striking harder. So in the second one, the temperature will change, which means the average kinetic energy will change. In the first one, the kinetic energy doesn't change, even though the pressure changes. Everybody clear on that? Any questions? Okay, that is it.